Okay, we're going to take a look at finding volumes, and over the course of this chapter we're going to find volumes of shapes using a few different methods. The method we're looking at today is by slicing or cross sections. Okay, so let's say we have a solid that has a circular base of radius 2 meters with square cross sections perpendicular to the x-axis. So it would help to have a visual to figure out what this thing looks like. So we can see here that we have this circle of radius 2, and these cross sections are perpendicular to the x-axis, and the cross sections are squares. So they extend from one side of the circle to the other side, and then they go up that same length, and you can see the shape that's created by this. So we want to find a formula for the volume of just one of these arbitrary cross sections with a width of dx. So notice that the little tiny thickness of each slice is going in the x direction, so that's dx. So we start with the equation of a circle, and let's get this into y equals forms. We'll subtract the x squared, take the square root, and we're just going to look at what would be the top half of that circle, y equals positive root 4 minus x squared. So that gives us the distance from the x-axis out to the edge of the circle. So to find the area of one cross-section, we need to double the distance from the x-axis out to the circle. So we need to go all the way across from one side of the circle to the next. So 2 root 4 minus x squared, and multiply that by itself to find the area of the square. So the volume is 2 root 4 minus x squared squared multiplied by the thickness dx. So that equation right there gives us the volume of just one arbitrary cross-section located at any x value. If we want to find the volume of the entire solid here, we need to go ahead and add all these up. And the way we add them up is by using an integral. So we can simplify slightly. Take the integral from negative 2 to 2 of 4 times 4 minus x squared. You can see here we changed our limits of integration to go from 0 to 2 instead of negative 2 to 2. And by symmetry, we then can just double the amount. So rather than 4, we have 8. Take the antiderivative and evaluate. And so here we have the volume of this solid created by square cross sections on the circle perpendicular to the x-axis. So in general, our method of slicing, we go through these steps here. We want to create some sort of a sketch and a sketch of the cross section. We want to know what this thing looks like. We want to find a formula that I'll call v of x. So that's the volume of one slice of this solid. Your book uses a of x. We use v of x because we're multiplying it by the thickness dx. Find the limits of integration, and then integrate. Okay, so we'll take a look at an example here. We want to find the volume of a solid with the base between y equals x squared and y equals the square root of x, with semicircle cross sections perpendicular to the x-axis. So that's a lot of information to take in. That's why it's a good idea to create a sketch. So that's our first step. And if you want to go and check out this website here, take a look and you can experiment around with what this would actually look like here in this case. You'll find that it looks something like this. So we have this region between y equals x squared and y equals root x, and the cross sections are these semicircles. We want to find a formula for the volume of just one arbitrary slice. So first of all, we know that the volume is going to be 1/2 pi r squared dx. We know it's dx because the thickness is in the x direction, and 1/2 pi r squared because it's half the area of a circle. Okay, so our radius is half the distance between these two curves, 1/2 root x minus x squared. Notice that root x in this case over this region is the upper curve, x squared is the lower curve. So volume is 1/2 pi r squared dx. So replace r with 1/2 root x minus x squared, and then square it, and we end up with 1/8 pi times root x minus x squared, all squared. The next step is to find the limits of integration. So we want to find where these two curves intersect one another. So root x equals x squared if x is 0 or 1. So if we integrate from 0 to 1, we end up with a volume of 0.0505. We'll take a look at another example. We have the base of a solid is the region bounded by y equals x squared, the y-axis, and the line y equals 3. And for this solid, each cross-section perpendicular to the y-axis is a rectangle with height 4 times the base. We want to find the volume. Now notice here, these cross-sections are now perpendicular to the y-axis, not perpendicular to the x-axis. So let's see how that changes things. So here's that curve y equals x squared. We're looking at the region bounded by x squared, the line y equals 3, and the y-axis. So it's that region up above the curve. And if we sketch a cross-section perpendicular to the y-axis, it would look something like this. And the orientation of this cross-section is what determines if we're using the variable x or the variable y. In this case, the thickness is in the y direction, so we have dy. So everything we're going to use now for writing our volume equation is going to be in terms of the variable y. So we need to solve our equation in terms of y. We start with y equals x squared. That gives us x equals square root of y. The volume in terms of y is the base, root y, times the height, which is 4 times the base, so that's 4 root y, dy. Take the integral, and our limits of integration are going to be y values, so this goes from y equals 0 to y equals 3. And we can simplify this one, take the antiderivative, and we get a volume of 18. And here's a theorem that can come in handy. If two solids have the same height and identical parallel cross-sections, they have the same volume. So we could have this cylinder right here, or we could have this shape. They each have the same cross-section, they each have the same height. These two objects would have the same volume.